Do you suppose that the Octonions have cosmic significance? Are you intrigued by mathematical physicists like Kolfiuri or John Baez, who are wondering how the Octonions may relate to quantum physics? I am taking the opposite approach. I have studied the metaphysical significance of what I call divisions of everything. I found an eightfold pattern that is reminiscent of Bott periodicity, and this is leading to the Octonions. So I want to present that work in progress today to my friend John Harland in Palomar College. We got our PhDs together at the University of California at San Diego. I am Andrius Kulikauskas. This is Math for Wisdom. So, John, here's the overall picture, and this may be kind of familiar to you. I've talked to you about Bott periodicity several times and recorded several presentations, but this one is for Octonian maniacs. So I have a lot to learn about Octonians, but it's just very intriguing how their pattern seems to be coming here. And that's the pattern here in red, which I'll decipher for us. And so this is Bott periodicity. These are the divisions of everything that I explain to you every so often, and you were visiting me in Lithuania. And so the idea is that there's certain, if you want to define complicated things, then you can do it in terms of simple things. But how do you define the simplest things? You have to define them with regard to each other. There's these relationships. So that's how you can talk to absolute truth if you have these structures of perspectives. So an example would be the learning cycle of taking a stand, following through, reflecting, and so on. Another example would be the never-ending dispute between free will and fate. So those are two perspectives that they make sense with regard to each other. And if you're thinking about free will, let's say good and bad coexist as opposites, then that can slide over to thinking in terms of fate, where it's all the same. And then the mind at that point doesn't really want to climb back. So that's another example of perspectives and how they shift. And then here in yellow is maybe harder to see, but it's four levels of knowledge: whether, what, how, why. And so especially like what, how, why, I think of them as the three minds. And so what would be the mind that unconsciously knows the answers? How would be the mind that consciously asks questions? And here, a why is full consciousness that does the investigations. And basically, consciousness is kind of like a break. Like you could have a perception action loop here between these two, the unconscious and the conscious. But when the unconscious has emotions, the conscious is trying to impose some kind of updated cognitive model, but the consciousness has a break. It says, wait. When your model is good, we'll feel peace. So wait until that. And then when it releases the break, then you go from how to what. And then the why is the break is released and you've gone to whether. So that's just a quick trying to introduction. So these are some of the very basic things that I'm looking for. And there's an 8 cycle of these divisions of everything. So there's 5 for decision making in space or time, where you have like a causality going in both directions, backwards and forwards. Every effect has had its cause looking backwards, but not every cause has had its effects going forwards. And there's a critical point for deciding, which could be the present, it could be a boundary. Then looking upon that present, there could be a conscience, theoretically. So, and I've drawn it like this. This is like a threesome with a relative and absolute perspectives. But you could also think of it as, and we'll see that this becomes very important. It's kind of like a frame, this frame of knowledge. So you're kind of building up like a first mind, a second mind, a mind looking upon the present, which would be like the conscience, and then a third mind. So with logic, so after you have morality, you have like, let's say logic. And that would be like a dialogue between a mind that knows and a mind that does not know. And so you could say, well, there exists a known and there exists an unknown. And so if you think of it starting as a state of contradiction, where there's no perspective, it's kind of relevant for talking about God, and then you have one perspective, so for everything, or maybe like when you're thinking about order, and then for existence, you need two perspectives, and then participation or learning three, and then knowledge, and then decision making, and then morality, and then logic. So what we're doing, starting with a state of contradiction where all things are true, we're layering these structures that prepare what you need in order to have a state of non-contradiction, which is quite sophisticated, subtle, but fragile. So if we added an 8, so this is the logical square, like all are good, I'll say all are known, all are unknown, there exists a known, there exists an unknown, there's these combinations. But if you added the fourth combination, all are known and all are unknown, well, those are opposites, so that means the system must be empty, and so the whole thing collapses, so you're back where you started. So this is something I figured out in 1989, after 7 years of thinking. I said, oh, wow. And you can have these operations which add 1 or 2 or 3 perspectives. So they kind of go +1 or +2 or +3 around this circle. And so I thought, that's fantastic. So then in 2016, I learned about Bott periodicity, which is also an 8 cycle. And I learned how it relates to, let's say, the algebraic topology of spheres, and spheres could be like perspectives. So the more I've learned about this, the more I've had this hunch that, wow, that's very central. I'm curious if it models this. So finally today I'm going to talk about the breakthrough with the Octonions, where I think it's clear enough to me. This must be this talking about the same thing, basically. So maybe to just say this introduction, I talked about this outer ring of structures. Bott periodicity has different forms. Most recognizable for people who know Bott periodicity is this sequence of homotopy groups, Z2, Z2, 0, Z, 0, 0, 0, Z, where so Z is the integers and Z2 is just simply 0 and 1, the group of size 2. And so, and it just goes round and round. And this is, if you look at the, one way to think of it is what they call geometrical, which basically says if you start, let's say, with orthogonal matrices, let's say they're 16 by 16, because we'll need the 16 dimensions by 16 dimensions. We're going to go through them. And then you have these linear complex structures, let's say J1. And we're going to basically, and I haven't written it here, but you can imagine J1, J2, J3, J4, J5, J6, J7, J8, and then you go back, and it's periodic. So once you've gone all the way around, you're kind of like back where you started. If you try to, so given the orthogonal matrices, you can, and I'll show maybe a bit more clear when I give the examples of the matrices. But if you have an orthogonal matrix J1, which is basically like 2 by 2 matrices. Maybe I'll just show what it looks like here. This is the key thing I'm trying to get to, is this picture here. This is what these matrices J1, J2, J3, J4, J5, J6, J7, J8 would look like. This is one realization. And so most important is J1. It's these 2 by 2 blocks, where the 2 by 2 block is basically the way of coding the imaginary number I. And so here I've written them as 8 by 8 matrices, but they could be going on as, as large as you like, let's say. And so what I'm saying, if you have, let's say, an 8 by 8 orthogonal matrix, and you ask yourself, is that matrix M commuting with just J1 or not? It turns out if M is commuting, then it has to be unitary, because it has to play nicely with these I's. So, and if it doesn't commute, that means that there's something that's not commuting with this, and so that would mean there's something that basically has a reflection in it, like a 1 minus 1, like complex conjugation. So that you can't do with linear complex matrices. So that's a way of stripping out from all the orthogonal matrices the unitary matrices. Those where these 2 by 2 blocks would be structured as complex numbers. That means that you'd have like an A here, and this, let's say, would be a B and a minus B. So those would survive, and the ones that don't would not. And then what you can do is you can keep going with another linear complex structure, but you would have to have it anti-commuting with this for this recipe. So that means that it would, in this basis, it would look not like this. There's some basis where it would look like this. I think there's some orthogonal basis where it would look like this. So it could be like this. This is like 4 by 4 matrices J, and it's repeated. This is, let's say, like negative K, and then it'll go on there. And then at a certain point, we're going to run out of 8 by 8 will be too small. We'll have to shift over to 16 by 16, and then I'll explain that. So why don't I go back to the beginning, and then let's see if you have any thoughts or comments. But what I'm trying to cover today is just to explain that this philosophical structure here, these structures, the Bott periodicity, where you start with the orthogonals, which basically that's what this is, ON cross ON modded by ON. So you could put the orthogonals, and then you say apply J1, what commutes? Well, it'd be unitary. And the stuff that doesn't commute, you can then construct this type of quotient, this space. Then you can continue, like, so let J2 be mutually anti-commuting. And then you could say, well, what survives would be this symplectic end, where you're looking at 2 by 2 blocks. And so you get the dimension halves. And then you get
Do you mean U of n or U of 2n on top?
I think it's U of 2n. You see, because these are isomorph. When I say symplectic of n, you see, it's gonna, just like here, orthogonal of 2n. These will group up into 2 by 2 matrices, and then you can assign those with entries in the unitary matrix. So we'll do the same thing here.
Okay.
So that's dropping the dimension. So that's why, like, typically you might want to start n equals 16 or a multiple of that. Then it'd be U of 8, SP of 4. And then you'd get like SP2 cross SP2. And then this would be SP2, and then it's be SP2 over U of 2, U of 2 over O of 2, O of 2 over O of 1 cross O of 1. And then you're kind of like, but you're back to O. So, so the point of all this is that when I followed the recipe in this wonderful, helpful paper by Stone, Chiu, and Roy at the University of Illinois, maybe from 2010, where they give the recipe for how to construct this J1, J2, J3, J4. And I kind of simplified that recipe just algebraically, just so it looks more. So it turns out you're really just using J1 and J2. You're using this isometry L, and you're using some diagonal matrices D, which you keep changing. And given that, if you just see it simpler like that, what you see is that you have J1, you have J2, you have J1, J2, but you have to tweak it with a diagonal matrix. Then you use an isometry L, and then it's starting to look like the Octonions, because J1, J2, and J1, J2, they're products, like the quaternions, Ij and Ij equals K, okay? Then this L, when you have the Octonions, it's kind of like a looking glass. And so things, if they're on the right side of L, they can pass over to the left side, and they'll have like, there's this kind of mechanics that goes on. And so this would be like the looking glass. It's kind of like you built up to the ceiling, and now from the ceiling, you're dropping down. So now that you have the L, you say, well, let's get rid of J1. So then you have something like this, J2. Then you say, no, let's instead get rid of J2. And we'll have this, LD, J1. Then you say, no, let's get rid of both of them. So then you just have LD. And then what do you do? Something happens, you get back to where you started, but basically it's kind of like this kind of eye creeps in. So I'll show you that. So that's why I'm talking about the Octonions. That's the pattern that kind of got me excited. Now, so one reason is simply that pattern, which I'll explain more about. And when I'm doing this, the whole point of this metaphysically is to take these concepts metaphysically and try to explain, well, how are they being modeled mathematically? So I talk about divisions of everything into so many, you're carving it up into perspectives. Well, so the orthogonal group O of 16R plays the role of that everything. That's what we're carving up, so to speak. Now, a perspective would be like these J1, J2s, and so on, J3s. Those are linear complex structures, and I'll talk more about that. A division of everything would be a set of such linear complex structures, a set of perspectives, but they need to be mutually anti-commuting. That means that like J1 times J2 is negative J2 and J1, and the same with any pair. Now, what's a shift in perspective? This is not quite clear. This is still something I'm wrestling with, but when I'll show you an isometry, L, which is the L here, it basically takes two different eigenspaces and maps one into the other, kind of like this mirror. So it functions like that kind of mirror. And so that'll be a shift in perspective, and basically it'll shift one axis to the other. It's actually going to be, that L is this big arrow here. It's taking one eigenspace, this, let's say, what and how, it's taking it to the other eigenspace, whether and why. So that's, and there may be, now the question is, how do you think of this? This somehow has to do, like if this is I and this is J, this sometimes has to do like, how is J related to I? And I'm still working on it, but we'll see that it could be kind of related like to this type of isometry or to charge conjugation, something like that. Now, a 3-cycle, this learning cycle, that's very important. And the question is, how does that come up? Well, then that's coming up in the quaternions, I, J, K, but in both directions. And the D kind of like shows that. So we'll talk about that. The foursome, like I said, is this isometry, I guess LD, and it maps J1, J2 from one space to another. And then these higher divisions, see, once you have this, and this is like a complete set, and you can think of knowledge as this mirror, that once you have, see, knowledge is something that can evoke a perspective. So the point of knowledge is that you don't have to have things in your mind. They will produce them as needed. So it's kind of like, once you have knowledge, you have this kind of like fullness of mind, and then you can have things that have kind of like building on that, right? Or it's almost like, this is building up with things that are like particles, and this is like holes, like what's missing. So once you have a full set, you can say, oh, I can have a hole here, or I could have 2 holes, or I could have 3 holes. It'd be like the 3 holes here. And so like, so what of the first mind could be 1 hole, the second mind could be the second hole, and the third mind could be the third hole. And so, you know, the third mind would be here, you know, combining these two or relating these two, balancing those two. So the second mind here would be like a conscience that watches you, let's say in the present. So that's very exciting. The whole Octonian thing is that you can think that some, like IJK, is about what is, and those are, let's say, like the particles that are. But the other IJK that relates with L, like LI, LJ, LK, those are the things that are missing, but they have their own quaternionic logic. So that's kind of exciting. So then did you get the higher divisions? And then the collapse of everything. There's a second isometry here that happens here, Q, and I don't understand it yet, but that's where we're up to. Any thoughts at this point, John?
Oh, it's a bit clearer now, I think, than when I've seen it before. I mean, I think your distillation, you know, the generators, you know, of the Clifford algebra, I think is nice, you know. So I think that's going to help. I mean, I think it's an advance on understanding how those come about. In terms of the mapping into the philosophy, I'm a little bit lost, you know. as usual.
Yeah.
Um, but um, but is so what is new now in terms of, I mean, you've matched these up before, right? The different structures, the divisions of everything with
Well, I think the
the Bott
progress made,
clock. Yeah.
you see like if and for those who've watched the sessions we've done, like in 2016, I saw, oh, there's this eight cycle. Okay, that's of course because I have an eight cycle and that's an eight cycle. I go, that must be interesting. I'm just curious. But then you start to learn about the eight cycle. It's like, oh, that has to do with spheres, mapping to spheres and things like that. Spheres are like perspectives. So it's like, well, that's not impossible that it could, be related to this. And then I start learning, oh, that this is at the heart of mathematics, like algebraic topology, algebraic geometry, um, analysis, differential equations, like, Lie theory, like this is the belly button of mathematics. It's all connected here, right? So then, oh, well, it's not a random place in math. But the question is like, well, okay, but even simple things like, well, how does this eight cycle match to my eight cycle, right? There's no way, you have to know where do they start, let's say. So getting the Stone Chiu Roy paper and then seeing that, oh, they have this J1, J2, J3, J4. You see, once you have
Right.
that, then you can say, okay, that's a perspective, that's the second perspective, that's the third. And you start to realize like how this thing is that's really carving up things. Now you could go in the opposite direction and basically get something very similar. I think the key difference would be, I think in this case, you're dealing with I, basically. You're dealing with
Yeah.
something that looks like this.
Yeah.
In the other opposite direction, you would be dealing with, it would not have this negative sign. It'd be the 1, 1. It'd be the swap, you
Okay.
see. So I think everything works kind of like backwards in the opposite direction. This is probably better for me because this squares to -1, and I've done a video before too, like where when you look at the Clifford algebra generators, you can, with Bott periodicity, you can be doing the things that square to -1, or you could do the things that keep squaring to +1, or you could mix and match, whatever. But it turns out, like, if you look at quantum symmetries, and then again, you'll have this like time reversal, you have charge conjugation. If they square to -1, that means it's a four cycle. It's something like I squared is -1, I cubed is -I out of the four. So it has this kind of like algebraic richness. Whereas if it only squares to +1, you see you lose that. So if you have that, it's like kind of like direct experience versus reflected experience. That's a theme. So squaring to -1 is more like reflected experience, and so it kind of like you're watching more. I think it's probably better, and certainly their tutorial focuses on that. So it's not even simple things like that, like which direction should you be going in? It's not clear. But so that was a step forward. But you see now, but still it was like, well, that's an eight cycle. I have an eight cycle. Now, of course, this three cycle and the quaternions kind of match up. There was like an isometry here that was encouraging. But see, once you see this L, and once you say, look, you're adding J1, J2, it's really just J1, J2. There's nothing more complicated. And then you just, taking them away. And there's this L here, and the L is like a mirror, like a looking glass. You see, once you have all that, it's like, well, shoot, like that's very similar to what I'm doing as far as I can tell, you see. So now you're really talking about things that just structurally, like whatever I'm doing inside my kooky mind, but it does seem like I'm always doing something very similar or, amenable or matchable.
Oh.
Um, and then to say maybe, so I think one thing to point out,
What
just
do these D matrices look like? Do you have a representation
yeah,
of them
these are here,
downstairs?
right here, I think. So maybe I'll just briefly say the Octonions do come up in proving Bott periodicity if you want them to. And so John Baez has a wonderful paper on the Octonions, and he has a little section, a chapter on how that happens. And so I won't talk about that today very much, but just to say that, and it has to do with the projective line. So like the real projective line, complex projective line, quaternion projective line, octonion projective line. You have to be careful because like quaternions are not commutative, octonions are not associative, so you have to use like Jordan algebras or be very sophisticated how you set up this projective line. And then these are like giving Hopf fibrations of different sizes. The classic one being the complex projective line, because then there you would have S1, S3 breaks up into S1 and S2, where S2 is the base space, that's like the how, and then S1 is the what, that's the loop. And so then you think of S3, which is in 4 dimensions, it's the 3 sphere. You think of that as built up of these circles, these loops, the whats, but organized by how. So like every point in the 2 sphere is a circle in the S3. See, so we're doing this with like S8 and S7 combined to get you S15. So what's happening here, and I won't try to bomb it, but like S8 is like it's like multiplying an octonion by octonion. So basically here it's like you have this isomorphism where you map X to an octonion X, you multiply it by L of 0 octonions. I guess X is in the, it's not an octonion, but it's in this KO, reduced KO theory, for the N sphere. The most difficult math, I think, at the time, probably, maybe even still probably up there. But it's just a simple map. So the octonions are definitely, it's for them to be there. So, the octonions are 8-dimensional, and maybe you're multiplying them by 7 dimensions or something, and you're doing this kind of thing. So that's him. There's an important paper, Geometry of Octonions by Eschenberg, and he's written an important paper about symmetric spaces that all can be studied. And this is a basis of the octonions. It's 2 sets of quaternions, kind of like, IJK, that L, and then ILJ, LKL. The thing being, though, that I'll show later the multiplication thing for L, how that works. But then also, like, this whole periodicity of Clifford representations, it can be done via the octonion. So he does that. So I have to learn that. And there's a periodicity theorem for Clifford modules, which is basically like representation. So M of n plus 8 equals Mn cross O squared. So tensored O squared. So this is the paper that I'm into. This is the geometric inclusion that you're familiar with. This is the parts of the tutorial. So in there, and you asked about the diagonal matrices. Here they are. So you see these diagonal matrices, the K would just be like -1, -1, -1, -1 on the diagonal, and then +1, +1, +1, +1. Okay. So then it could be mixed up. It could be like M would be -1, -1, +1, +1, -1, -1, -1, +1, +1. Then it's like alternating everyone. -1, +1, -1, +1, -1, +1, -1, +1. And then here you run out of room. So then what you do is you have to kind of make it 16-dimensional. But you can't do it, it turns out, or I wasn't smart enough like to do it by doubling. You have to do it by breaking up each, rethinking each one as a 2x2 matrix. So like this 2x2 matrix, like R hat would be taking a 1 and then replacing it with this 1 minus 1, 0, 0, 2x2. And then I hat would be replacing it with this. So if you do that, then the diagonal would be like, it's basically like a, it's like a 1 minus 1 on the diagonal, like 1 minus 1, 1 minus 1, and you reverse it. So it's -1, 1, -1, 1, 1 minus 1, 1 minus 1, -1, 1, -1, 1. And then this Q would be the isometry, the second isometry, L being the first isometry. So the isometry looks like this. So here you've got an I4 minus I4. You're swapping 2 eigenspaces. And you're swapping them with a sign. And so what that'll do, it'll take like if you have eigenvalues plus and minus 1, you have a space where 1 is an eigenvalue. It just fixes it. Whereas the other one, it's -1 is the eigenvalue. So it swaps it back and forth, -1. So this type of matrix, it'll take your V plus on top and it'll map it to the V minus on bottom and vice versa. Okay, so you can do the algebra to figure that out. So that's what these diagonals. So there's something going on here. It's not doing nothing, but on the other hand, it's doing something that is of limited complexity, right? Like, so that's the code to crack.
There's only so many possibilities.
Yeah, and somehow it's running out of possibilities, and so instead of doubling, you're forced to tensor somehow. And they talk, so the stone thing, first of all, like you've seen his paper here, basically. I can just show it, like, so he'll look at something like this, blah, blah, blah. So I, I, um, I'm just kind of gotten the part, maybe most important for me. He says, okay, you start with J1 is just diagonal. Let's just go back. Well, it's the I, and then this is be like the J for the quaternions on the diagonals. And just to kind of say for maybe those who haven't, like, what we're trying to do is define J1, J2, J3 that are orthogonal matrices. So J alpha times J alpha transpose is identity. They're going to be independent generators. That means not only are they linearly independent, but also like in terms of Clifford algebra generators, they need to be independent Clifford algebra. So we'll run into this problem that like, well, I times j is k. Why can't we use k? And the problem is because, well, k is I times j. We've already got y, we've already got j, we've got their
Right.
product. If you want to go further, you have to come up with something new. So that's a constraint. These got to square to -1. And that implies that then that the inverse is going to be the negative. So they're skew symmetric. And they have to be mutually anti-commuting. And so what mutually anti-commuting basically says is that it ensures that they're different, because if it was J alpha times J alpha equals negative J alpha, that wouldn't work. So this is a mutually anti-commuting condition that it kind of ensures them being different. So the way he does it, and he uses this fact that's important. If you take J1, so J1 squared is -1. But if you go J1 times J2, you square that, that's also -1. Because if you take the 2 over, that's anti-commuting. And then they each square to -1. So that's odd. That's three -1s is a -1. But if you have J1, J2, J3, and you square that, you're going to get a +1. So because you'll shuffle 3 times and then you'll square 3 times. And so that'll, be 6 actions and that'll give you +1. And then that means that you have an operator, J1, J2, 3, that satisfies that if you square it, subtract 1, you get 0. And so that doesn't factor the operator, but it does mean that the eigenvalues factor. And so that means that then you know that the eigenvalues are plus and -1. Those are the only eigenvalues you can have. So the problem is that you don't know how many there could be of them. What you do kind of realize, though, is that they can't all be 1 or be -1, because then you'd be back in the situation where, let's say, like J1, J2, J3. Well, basically, where like J3 would just be the product of J1, J2, or plus or minus,
Yeah.
So you need both in order to run out, get out of that problem. He doesn't really kind of mention that, I don't think.
You need both what? I'm sorry, I lost the thread.
You have to have both eigenvalues
Oh,
existing
okay.
for this to make sense, because otherwise you're not going to, then J3 isn't independent of J1 and J2. It could be just the product or the negative of the product. So anyway, so he does it all backwards, and I'm doing it much more concretely because I'm trying to get a concrete realization, because that's how
Yeah.
my puny mind works.
Right. Yeah.
But so he does, like, suppose J3 exists, then you have this
Right.
operator.
Yeah.
And so, all these operators are these triples, because then they do that kind of breaking up into 2 eigenspaces.
Okay.
And see, then the important thing for us is that we can use that to figure out, define J3 concretely. So you kind of have to monkey around, as I did, well, what's the K that will work? Okay. So the K's was like, well, you put -1, -1, -1 on the diagonal, and then you go 1,
Yeah.
1, 1, 1. See, so once
Right.
you have that with J4, now you have to assume that they both have the same dimension, these eigenspaces. And then you say, okay, suppose J4 exists, let L equal J3 times J4. So L is going to basically look like L will look like this. So K looks like this, I to the fourth or minus I to the fourth. I may have gotten the sign backwards, so I have to kind of, been inconsistent about that. I have to check. But anyways, or maybe not. Yeah, here I've written it like this for some reason. Then L would be this, and then you multiply them, then you get the swap, right? So this is kind of like, and so this, with 2 by 2 matrices, you have the identity, then you have reflection, what I call, or like conjugation. You have the I, that's rotation, or the negative of it. And then you have the swap. And the swap is the product of, let's say, reflection. Let's say it's I times reflection, I think. It gives you this kind of swap. So KL is this. So he's doing this very abstractly, but basically, concretely, it kind of looks like that.
Okay.
And the crucial thing is that this L preserves the quaternionic structure. It's a quaternionic isometry from V plus to V minus. And then you can use that to define J to the fourth, right? J sub 4. So J sub 4 is going to look like, so basically what we have I complex, but also quaternion I on the diagonal. We have these J's, and we have the K. But here, what we do is I think we have to put negative K and K, and that will keep it from just being J1 times J2. But it'll work, like you'll be able to get the logic to work for the Clifford algebra. Then this J4 is what you get. Basically, this is a K on the top diagonal, and this is another copy of K on the other diagonal. Does that kind of like 1, 1, minus 1, minus 1, that's a K in quaternionic language. 1, 1, minus 1, 1, that's a K. Then these are going to get split up. What's going to happen with the J5 and then J6, you're kind of like, once you have, I could probably go back. We built up, unitary, like we built up the complexes, we built up the quaternions, that's what the symplectic's about. We split that into 2 parts, that was where the K was in. Then we showed that, okay, there's an isometry between them, and then we can look at the diagonal space, okay? So that's giving us, this is basically the symplectic, SP of n cross SP of n over SP of n. It's saying there's a copy in here and in here that's the same. So that's the diagonal. So that's the mapping from the one world to the other. And so that's where this L's coming in. You see, so this L in this Octonion language, this L is, it looks like this. It's the thing that's relating the 2 worlds on the swap. So all these matrices here are now having, the other ones were on the main diagonal. Now these are on the off diagonal. This J4, J5, J6, J7. They've all got that L built into it. Okay?
Okay.
Swap in the swap. And then here, like he was doing, he was building J5. Okay, so this M is another reflection matrix. So all these M and N and P, these are diagonal matrices. Basically, they're built up of reflections. They're just organizing them into finer and finer units. And so he keeps doing it. And see, now what he does, he goes, okay, when you get these eigenspaces, you see it's going to be W minus equals J2 W plus, or it's going to be X minus equal J1 W plus. So what they're doing is they're basically they're undoing the structure we've built up. They're swapping things. So I think the way it works is like with this J5, when you have a quaternion, it's a 4 by 4 matrix, and you can think of it as built up as 2 complex, it's a complex number times a complex number. So you would have like, 1 plus I plus, let's say, 1 plus I times J, something like that. You'd have a scalar plus I times a scalar, and then you'd have a scalar plus I times a scalar times J.
Right.
So that gives you a J and a K. Now, if you have a, if you allow yourself to take those 2 complex numbers and swap them, but if you're true to the inside, like you don't move, you keep the the 1 and the I together, basically,
Okay.
right?
You keep the integrity of each separate complex number. The
then
identity.
it's gonna stay complex, but you're gonna lose the integrity of the quaternion. And
Okay.
so that's what this J5 is basically doing. And so in the same space, that you had, let's say these symplectics, you see, now you're gonna have unitaries in there. So why does that take, oh, but see, you're gonna have unitaries of the same dimension. So you're using the same size matrix. I'm a little confused, like how this dimension is. Well, why don't we look here? A crucial thing about this, the Clifford, see the matrices, the size of, this is the crucial thing, J6. You can see how these are building up. J1 yields the complex numbers, right? J2 yields the quaternions, right? Because you have J1 and J2.
Okay.
J3 yields H plus H, because you're going to get a quaternion copy up on the top here, and then a quaternion copy on the bottom here. But once you have the off diagonal, now you're going to get quaternions and a 2 by 2 of quaternions. So it'll be 2 by 2 matrices of quaternions, right? Now, when you destroy that integrity, you're going to get not quaternions anymore, but you're going to get 2 by 2 matrices of complex numbers. So this will be a 4 by 4 of complex numbers, right?
Okay.
And if you do that same trick with the reals, now you're going to get 8 by 8 of the reals. So the powers are growing by 2. You know, complex has 2 dimensions, quaternions has 4 dimensions, H plus H has 8. 2 by 2 of quaternions has 16 dimensions. This will have 32 dimensions. And then this will have 64 dimensions when you get to, which is what an 8 by 8 matrix should have, right? Like, so that's kind of telling you that at this point you've used up every single kind of nook and cranny of this 8 by 8 matrix algebra, right? But
Okay.
you've done it with by building up these Clifford algebras. So you have nowhere to go. So now you need to do like 8 plus 8, and then you'll do 16. So if you try to, and I tried to do this and it doesn't work, like if you tried to do the same trick, you'd go, okay, let's do the J7 and let's figure out what this P, what this P has to be and calculate it. The point is that you want it to commute with, you want it to anti-commute with all the J1, J2, J3, J4, J5, J6. And the problem is it won't. So if you define J7 by just making it bigger, let's say you just have 2 by 2 blocks, or that are 8 by, you have 8 by 8, 2 8 by 8 blocks on the diagonal. The problem is that these will all be built up out of reflections. And when you try to commute that with the J element, that was a reflection and a minus reflection, and it goes on. You can't get reflections and reflections to not commute, at least not this way that I'm doing it. So then you have a problem. So what you have to do is you have to go and say, no, I'm not going to make the matrix twice as big. I'm going to replace each unit with a 2 by 2 matrix. So you're tensoring in a certain sense. So that's what they do. And so then it turns out like I calculated these out, and these are all anti-commuting, and they all square to -1. They all satisfy what needs to be satisfied. So maybe just to kind of conclude,
Why does that bring us around back to the top of the Bott clock? Where
see, I don't know. That's the problem, is I have to figure out like, all I've managed to do is to calculate this.
Okay.
So maybe the things I want to wrap up with to show is that, here's just calculating like H plus H, what do these all look like. An important thing to say, Louis Kaufman, he has a nice thing with his student Hackett, where they did the belt trick. See, the belt trick models the quaternions. But if you have a belt with a
Louis
loop,
Kaufman, your friend,
I just knew him. He was nice to me
no,
when I was
like
visiting him.
he came to your art show, right?
He came to my art show. Yeah.
Yeah.
I wish I was in touch with him.
Yeah.
He's definitely like in the thick of all these things. But he has a very nice way of looking at the octonions, you see. And so there's different ways of looking at the multiplication, but that mirror, L squared equals -1. So you have this mirror where like L takes A, and if A passes through the mirror, it becomes negative, right? but also like on the right side of the mirror. If you go L times A, L times B, you get L times BA. When you have parentheses like that, it switches the order on this side of the mirror. So if you're staying on this side of the mirror, but it'll switch the order when you multiply.
Okay.
If you go, okay, and then you have LA times B, I think that's the same thing. Yeah,
Okay.
that's probably just another way. Oh, that's just not, it doesn't matter if it's an LB or a B. It's just kind of going to put it there. Now, if you have A times LB, you see, it will hop over in front. And so, so if you cross the mirror, you cross over the whole thing. You go from the one side to the other side. You hop over the B. So the point is that LBA, you can look at it in two different ways. You see, LA times B is LBA, but A times LB is also LBA, right? And the point is that typically, oh, and this is LBA. See, LA times LB. The point is that this is not going to be associative if you have this type of mirror at play, because LA times LB, that's LBA. So, oh, because you don't know which one you're talking about. Oh, because L times BA, is that going to be the same as LB times A? Oh, well, let's put it this way. See, L times BA is generally not the same as L times AB, right?
Okay.
But see, this is equal to that always. So it can't be associative. L
Okay.
times parentheses BA is typically not going to be L times parentheses AB. But this is equal to that. So that means that it's not going to be associative usually. So that's a very nice way to kind of see that. In the belt trick, this L is serving like this kind of like loop or sphere that can get shifted to across to the other side or whatever. But the thing I wanted to say was that this is now the thing to do, is to go back to my most recent video with you and Thomas on the Clifford algebras. You see the quantum symmetries. Because these things here, those diagonal matrices are these things here. Those are the time reversal. They're reflections, you see. So those are the time reversal symmetries. So those are clear. The C is charge conjugation. I think that that's basically like this swapping, you see. So I think it's like that L, something like that. And so what's happening here is you can kind of see like when do they exist or not, these different symmetries? What are they squaring to? Like in the case of reflection, they're all squaring to +1, which is as they should. But so when reflection's over here, it's squaring to -1. It's like J2, J3 is considered a reflection. Those square to -1. But so let's look at what that reflection looks like. J2, see 1 minus 1, that's a reflection. And then it's reflected. You see 1 minus 1, that's a reflection. And the same thing, J3, like I guess 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Like those are reflections, but they're organized in a different, there's something happening to them which keeps them from, it's not a simple reflection like in the case of those diagonal stuff. So here in their discussion, they're going to talk about, seeing this I is basically like that tensor product. See, this is the J1, 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 and then they change it with this 2 by 2 matrix. They change it with an I that's basically like they're doing this kind of tensoring that basically I was doing, and then they kind of like cover it up. They're doing something kind of sneaky here, but it allows them to go in the way that I want to do, like not make things bigger and keep going infinitely bigger, but to say there's some kind of little contradiction, so to speak, that enters in, but it allows you to walk through the whole 8 cycle. So I still have to figure that out. So now I should go back to studying this paper. I should go back to, I should learn about I need to keep trying to understand John Baez's on that projective octonionic, but I should study Eschenberg's stuff and on symmetric spaces. But
Well, and also that final step in the Bott clock, just from the point of view of algebra, just from the point of view of matrices, that would be interesting to understand in a little bit more detail.
I want to show that because that's what they talk about here at the towards the end here. Okay, so here's what they call the discrete symmetries. See, it's all about a Hamiltonian. So that J1 is basically like multiplied times M is a Hamiltonian, so to speak. And there's different kinds of Hamiltonians with different quantum symmetries depending on where you are in the cycle. See, so what they do is they kind of say, like, when you start off with the whole orthogonals, they basically say, okay, these coset generators M, which is what the Hamiltonians are if you multiply it times, these are not diagonals with others. We need to double the Hilbert space and tensor with I equals and I sigma 2 Pauli matrix. That's basically, I think, 0, -1, 1, 0. That's that matrix. So it's exactly what I'm doing here, so that the Hamiltonian becomes this cross M, you see. Then taking phi, I think that's the swap matrix probably, like to be the real structure that defines complex conjugation, we have this equals that. See, so they're building that in, and then they're going to go, then they go, as they go through a couple steps, they go, oh, we can keep C equals phi as particle symmetry and take tau. See, so these quantum symmetries are going in and out. Sometimes T is in there, sometimes charge is in there, sometimes they're both in there. And what it does, it kind of gives you like two hands so that you can let go and then grab with the other hand. And so it kind of allows for this contradiction to happen, basically, I think. I think that's what there's this kind of like sleight of hand here. This is like magician sleight of hand that's happening here. And then they go kind of like the generators are real skew matrices that commute with J1 and anticommute with J2. They can be regarded as skew quaternion Hermitian matrices with complex. We no longer need set I to -1 as the matrices no longer have elements coupling between the artificial copies. We instead use, so there's something funky going on here, which I think is
Yeah.
addressing the whole issue. And then
Okay.
at the very end, they say something like, the problem here is that what to take for I, as the current H goes to J1n, will take us out of the eigenspace of n. But this is the problem we started with. We need to double the space and keep I equals J1, and the real structure. What are they talking about? I have to figure out. But see, now it's concrete enough to where it's possible to
Yeah.
say.
To get a handle on that. Yeah. Yeah. Nice. I think you're definitely homing in on this, So yeah, I'm looking forward to having some time to jump in with you to flesh all this out. Do you want to stop the recording at this point?
I just want to thank everyone who's watching. Maybe you're going to become an Octonian maniac like I am, because this is at the center of all math. And, so if you've placed your bets on Octonians, maybe you will win. I want to thank John, and I just want to end with a prayer to say, I'm very blessed to have your friendship, and I'm very blessed that people could care about this. But I just feel the love of God that, to be able to work on this for 40 years and then to feel like, oh, maybe this, it can be validated or connecting with, the whole belly button of math. I'm just very excited. So thank you for being with me.
Nice. Okay.
Okay.
This is John Harland. I'm the leader of the physics study group for Math for Wisdom, and I'm a Patreon supporter of Math for Wisdom because these conversations have been very helpful for me. It's a way of engaging with people with different points of view, kind of not so much in my own echo chamber, but engaging, kind of a wider set of ideas. And so I want to keep it going, so I'm a supporter. And
Thank you for watching this video. Please go to mathforwisdom.com or simply read the description to this video to learn how you can join our Math for Wisdom discussion group and our study groups. Thank you for liking this video, for subscribing to this YouTube channel, and for supporting Math for Wisdom through Patreon.